Welcome to physics online session. In the previous class, we have discussed the structure and working of human eye, and with the naked eye, without the help of any optical device, we can see the objects around us when they are placed between the infinity and near point. Okay, so what is the near point? It is about 25 centimeter in normal distance for clear vision. Near distance for clear vision. Okay, if the distance, if the position of the object, if the object is positioned less than this distance, we cannot see them clearly. So we need some optical devices to see them clearly. Okay, but with a naked eye, when it is at 25 centimeter, or when the object is placed in between infinity and 25 centimeter, we can see them clearly and distinctly. Okay, so but with the aging, what happens? The ciliary muscle weakens, not only with the age, but also some certain other factors also decides the weakening of ciliary muscles. Okay, so due to the weakening of the ciliary muscles, some defects in the vision arises. Okay, already we have discussed those defects in the previous classes. So that is myopia. So the person who is suffering from myopia can see only the nearby objects but cannot see the distant object, and this type of defect can be corrected by using a biconcave lens. Okay, and the next defect that was discussed is uh, hypermetropia. So the person who is suffering from hypermetropia can see the distant object but cannot see the nearby objects. So this type of defect can be corrected by using a biconvex lens. Okay, there are two more defects. One is presbyopia. Okay, this presbyopia defect arises with the aging. With the age, ciliary muscle naturally weakens. Okay, so this is actually, it is a combination of both myopia and presbyopia. The person who is suffering from presbyopia can see both the nearby and distant objects, and this can be corrected by the combination of convex and concave lenses, suitable combination of convex and concave lenses, and that combination is known as that lens combination is known as bifocal lens. Okay, and the last defect that was discussed in the previous class is astigmatism. Astigmatism, a person who is suffering from astigmatism cannot see the actual shape of the object. He will see the distorted image of the object, and this type of defect can be corrected by using the cylindrical lenses. So these are the topics we have discussed in the previous class. In this class we will discuss the construction and working of microscope and telescope. Before going to discuss microscope and telescope, so we'll discuss some basic concepts so that we can you can understand the structure and working of microscope and telescope. No, when you see the objects around us, some objects looks bigger, some objects looks smaller. So why they appear smaller and bigger? Because the size of the object that depends on the angle that it's obtained at the eye. Okay, if that object is making large angle, so it looks bigger. If the object makes a small angle at the eye, then it looks smaller. Okay, so the size depends on the angle made by the object at the eye. Okay, here I took three objects here. Okay, so here I took three different objects of different heights. I'm placing those three at the same position. Okay, first I will place object I have height h1. Forget about the second and third object. Okay, and this object I'm taking one light ray from this tip of the first object, and when it passes through the eye lens and focuses on the retina at this position, so and this is the angle made by this first object at the eye. Okay, and remove the first object, and now place the second object of height h2. Okay, and if you take light ray from the tip of the second object, it come to focus at this position, and that angle uh, made by that object is theta 2. Remove the first and second objects, and now place the third object of height h3, and I'm taking one more light ray from the tip of the uh, this object, so it makes it come to focus at this point. So since the bigger object certain large angle, so it looks bigger. Smaller the angle, small is the size of the object. Okay, so larger, what is the conclusion? Larger objects subtend larger angles, smaller objects subtend smaller angles, so they look small. Okay, let us take another situation where the same object placed at a different distances from the eye. Okay, so initially when the object is located at I3, so here the angle subtended by that object when it is at O3 is theta 3. Okay, as it comes close to the eye, the angle subtended by the object increases, and when it is at a near point, the angle subtended by that object is maximum. Okay, so let us take an example. Aeroplane, when aeroplane is in the sky, when it is flying in the higher at a higher altitudes, it looks very small. Why? Because the angle subtended by the aeroplane is small. When the same aeroplane flying at a lower altitudes, it looks somewhat bigger. Why? Because the angle subtended by the aeroplane is large. When it is on the ground, same aeroplane, when it is on the ground, so it looks bigger, very big. Why? Because the angle subtended by the aeroplane is large. Okay, here the size of the object is constant, but the angle subtended by the same object at a different location is different, and that is why the same object at different location looks differently. Okay, remember this point, the same object at different positions subtend different angles at the height, so it looks in a different sizes. Okay, it appear in a different sizes. Let us take one example. When your eye is focusing the distant object, when the object is at infinity, the light rays which are coming from the that object almost parallel. When the parallel beam of light allowed to pass through the eye lens, so they automatically come to focus exactly on the retina. This is a normal setting of our eye. Okay, so here ciliary muscles are in a relaxed position, they are not compressing the eye lens. Okay, they automatically come to focus on the retina. Okay, here the ciliary muscle are not doing much work here. Okay, right, now this is said to be a relaxed eye. Okay, when you are focusing the infinite object at infinity, our eyes feels relaxed. Why? Because the strain on the eye is small. Why? Because the ciliary muscle are not doing any work, or not compressing the eye lens. Okay, so the next when the same object uh, when the object, not same object, when an object is, when any other object is placed at a near point. Okay, near point, how it looks to us. Okay, when the object is placed at near point, what happens? So here the light rays are not parallel. Here in this case the light rays are not parallel. If they are parallel, exactly they would come to focus on the retina. Actually these are not parallel. Okay, the dark color here, black color one, is the actual size of the eye lens. Okay, but when the object comes close to the eye lens, what happens? Ciliary muscle compress the eye lens. The red color lens represent the new position of the lens, new shape of the lens. It is in a compressed state. Okay, so here when it is when it is in the compressed state, the strain on the eye is maximum. Okay, no, the eye is said to be in a under strain. Okay, no, it is a strained eye. Just remember 2 points here. So when it is, sorry, uh, when you're focusing a distant object, so our eyes feel relaxed. When you focusing a uh, nearby object, our eye feel strain, and the strain is maximum when the object is at near point. Okay, now let us find out what is angle made by sun and moon at the eye. Okay, before that, I want to tell you one point here. The angular resolution of human eye is about 10 power of minus 4 radians. Okay, so you will come to know what is angular resolution in the next chapter. Just in this chapter, just try to remember the value here. The angular resolution of human eyes is in the order of 10 power of minus 4 radians. Okay, so here this is a moon, and let L be the distance of the moon. Actually the distance is about 3.84 into 10 power of 6 meters, and the diameter of the moon is about 3.85, around 3.85 into 10 power of 4 meter. Okay, and it is in the order of actually 10 power of 10 power of 4. Okay, and it is in the order of 3.85 into 10 power of 6. Okay, okay, and this is a moon, and subtend an angle theta at the eye by using trigonometry relation. Tan theta is equals to opposite by adjacent. We can, from that relation we can find the angle, that is tan theta is equals to d by L. When the angles are very small, so we can approximate tan theta to theta, and theta is equals to d by L. So d by L, d is the diameter, it is in the order of 10 power of 4, and the distance between the moon and the eye is about 3 into 3.85 into 10 power of 6. So you will get the angle subtended by the moon about 10 power of minus 2 radians, which is much bigger than 100 times bigger than the eye resolution. So that is why moon and sun looks bigger to us. So both sun and moon subtend the same angle at the eye. Okay, that is why they looks in the same size. Okay, right. Let us take another example. uh, the smaller objects like bacteria and distant objects like stars subtend angle less than 10 power of minus 4 radians. That is why we cannot see the bacteria and stars clearly with a naked eye. Okay, so in order to see them clearly, so we need some optical devices. Our eyes cannot see them clearly, therefore some optical devices, like in order to see smaller object we need microscope, to see distant object we need a telescope. Okay, so this is the importance of microscope and telescope. They actually increases the angle of vision. Okay, the microscope and telescope increases the angle of vision, so they look bigger. Okay, next, now in this class we'll discuss structure and working of a microscope. Here in this class we'll discuss the simplest microscope that uses only one lens. Okay, so here here a convex lens of small focal length acts as a simple microscope. Just it uses only one lens, that is a convex lens. Okay, this is a simple microscope. Okay, so in order to view the small object, the object must be close to the lens. Look at this picture. So he is looking the a smaller object, bacteria like that. So in order to see the small object, this is the object, position of the object. So to see small object, the object must be close to the lens. Object must be positioned close to the lens, and the eye and eye must be positioned close to the lens. Here eye is also close to the lens and object is also close to the lens. Okay, this is the compound microscope, but the same thing will happen in the simple microscope also. So in order to view the small object, okay, this condition must be satisfied. We need to place eye close to the lens and the object also must be placed close to the lens, then only we can see it clearly. Okay, now uh, so when the object is close to the lens, okay, so we'll get a magnified image of that object. So look at the last row of this table. When object is in between f and p, when it is very close to the lens, the object is located between the focus, let it be the focus, and this is the optic center. An object is placed between optic center, let it be O or P. So we'll get the image on the same side, the magnified, erect and virtual image on the same side. Look at this picture. Okay, this is an image and this is an object placed close to the lens. You will get the magnified image. Okay, so that we can see it clearly and distinctly. Okay, and the next here we'll discuss the magnification produced by the convex lens when the image of the smaller object, the image of the smaller and nearby object formed at the near point. Near point is about the about 25 centimeter. It is the least distance of distinct vision. Okay. Now here we'll find out magnification in one particular case when the image is formed at near point. Okay, so we'll adjust the position of the object. We'll move the object in between focus and optic center so that image is formed exactly at 25 centimeter from the eye lens. That is about a normal near point. Okay, now so what about the formula to find linear magnification? It is a ratio of distance size of image to size of object, or distance of image to distance of object. Okay, so where the object is located, here it is placed close to the lens, let it be the focus. Okay, so when the object is placed below the focus, then only you will get the magnified image on the other side. Okay, that is why focus must be on the left side of this object. This is an object, this is an object. So here the object distance is u and the image distance is v, and our intention is to get the image at this distance, but actual distance, image distance is measured represented by letter v. That is why so magnification can be written as m equals to v by u. Okay, now I want to rewrite this expression by using lens formula. What is the lens formula? 1 by f equals to 1 by v minus 1 by u. I want to take 1 by u common from this expression. You will get 1 by v minus 1 by f. Now by substituting 1 by u value in this expression, you will get m as m equals to 1 minus v by u. Okay, so where u is the object distance, v is the position of the image, and our intention is to get image at the near point. So v, when the image is formed at the near point, the image distance is nothing but v equals to minus d. Why distance d is taken as negative? Why? Because it is measured opposite to the direction of incident light. Okay, so we'll get a magnification as m is equals to 1 plus d by f. Okay, so already in the previous slides I told that when you are focusing, eye is focused at the near point, it causes more strain on the eye. Okay, So that is why the position is said to be uh, strained eye. Okay, this is a magnification under strained eye. Okay, now we'll discuss one other case where the image is formed at the infinity. Okay, so here when the image is of the object is formed at infinity, so what would be the magnification? Okay, here here I will use angular magnification formula, not linear magnification. Why? Because I don't know the position of the object. I'll use angular magnification. So this is an angular magnification formula. So magnification, it is the ratio of angle subtended by the image to the angle subtended by the object. So just we need to find the values of theta I and theta naught. So we'll get angular magnification. Okay, theta naught is the angle subtended by the object. Okay, without any lens. Okay, at the eye is nothing but the theta I. So this is a object, a smaller object. So and by this triangle we can write tan theta naught is equals to opposite h by d, opposite by adjacent. Okay, but this is a small object. The height of this object is very small. We are observing the bacteria, the size is very small. It is in the order of 10 power of minus 6 meters. Okay, it looks small. So it is small, the height is very small, the h is very small. The smaller angle, the angle made by the object also very small at the eye. Okay, that is why it is approximated to theta. So therefore tan theta naught equals to h by d. So we can write theta naught equals to h by d. Let it be equation number 1. Now we'll find theta I. Okay, so here let us assume h and h dash are the angles, are the heights of the objects and images, object and image. Then the magnification will be, this is a general formula to find magnification: ratio of heights or ratio of size of image to object distance. Okay, look at this picture first. Okay, here this is an object, and this object is placed at focus, exactly on the focus, at the focus. When object is at the focus, the image of that object is observed at infinity. Okay, so it appears to be coming from infinity. Okay, you know, when the object is at the image is formed at infinity, we don't know the height of the image. That is why I want to express the heights of image in terms of height of object. I am taking h dash common from this expression. So my intention is to find theta I. Okay, what is theta I? Theta I is equals to uh, and it is theta I is equals to h dash by this v, actual expression. Okay, tan theta I. So we don't tan theta I. What is theta I? Angle made by the object. Tan theta I is equals to, okay, height of the image. Where we got the image? At infinity. We don't know h dash. What is the height of the image? And we don't know the position of the image. So we need to calculate this relation. We don't know h dash and v. So we have to replace um, h dash and v with another terms. That is why in the first case I replace h dash with v by u into h. So see the next step here. So let us take an angle. So already I showed here tan theta is equal to h dash by v. Now substitute the value of h dash and you will get this expression. So this v, when you substitute the value of h from the previous expression, so v and h dash are removed from that expression. So what do you get? Theta I as h by u. Okay, v and v got cancelled. It is the denominator, it is the numerator. So we will get theta I, angle subtended by the image at the eye now is h by u. Okay, it is in the presence of the lens. Theta naught is in the absence of the lens. Okay, so and what is angular magnification produced by the lens? It is theta I by theta naught, that is equals to, by simplifying it you will get d by u. Okay, since the image is formed at infinity, definitely object must be located at focus. Yes or no? When object is located at the focus, then only we will get the image at infinity. Okay, therefore u must be equals to f. Therefore the magnification in this case is d by f. Okay, when you are focusing a infinite object, it looks our eye feel relaxed. Okay, right, this is another magnification. Okay, so now this simple microscope, with the help of a simple microscope we will get a magnification in the order of 10 only. Okay, just look at the uh, expression. So here magnification is inversely proportional to the focal length. The distance is fixed here, so it depends only on the focal length. Smaller the focal length, greater will be the magnification, but there is a limit to fabricate the lens. Okay, you cannot construct a fabricate lens of any size. There is a limit to this size. Okay, that is why with a simple microscope we can get a magnification in the order of 10 only. Okay, we can magnify the uh, uh, image by 10 times, object by 10 times. Okay, next for larger magnifications we use combination of lenses. Okay, so here this is a simplest compound microscope. It uses two lenses. The complex microscopes, there may be more than two lenses. Okay, in this case we are using two lenses. So this compound microscope consists of two lenses which are placed coaxially. The principal axis is same for the lenses. Okay, so one of the lens is known as objective. One of the lens is said to be the objective. So the objective, the lens which is close to the object, this is an object. The lens which is close to the object is known as objective, and the lens which is close to the eye is known as eyepiece. Okay, so here in this case also we'll find the magnification produced by the compound microscope. Here the second lens compound the effect of the first lens. That is why it is known as compound microscope. Okay, so here this is a situation where the final image is formed at the near point. This is the final image, so it is formed at the near point. Okay, so here we will find the magnification first magnification produced by the objective and then eyepiece, and finally we will find the magnification produced by the total lens, combination of lenses. So here the linear magnification produced by the objective is general formula to find magnification h dash by h. Okay, here look at the picture here. This is a height of the object and this is the image produced by this lens. Okay, so therefore magnification produced by the objective lens is the ratio of heights h dash by h. So here the object is placed just beyond the focus. Okay, if the object is placed below the focus, the image will be obtained on the same side. Okay, but it is not our case. We need to get image on the other side. Okay, that is why the object is placed beyond the focus. When you place an object beyond the focus or in between center of curvature and focus, you will get the image uh, beyond the center of curvature. Here look at this object, so we got an image here. Okay, what is the magnification? So magnification here h dash by h. Okay, here what is the height here? This is the height, and since the ray we have taken one parallel ray, So this height also, h. Here I am taking, I will represent this point with O dash. I will take one right angle triangle here, O dash and F. Okay, this is F. This is F naught. Why? Because the parallel ray of light, this is the parallel ray of light, after refraction from the lens, come to focus at a point. That is the focus. This is a focus. This is F naught. Okay, this is F naught. Let it be O and draw a perpendicular line here. So now we got a right angle triangle here, and the same I representing here. That is, this is O optic center, and this is, let it be O dash. Now from this we can write tan beta. Tan beta is equals to h by f. Since h is very small, tan beta is approximated to beta. So, and we'll write tan beta is equals to r approximately beta equals to h by f. Okay. Similarly, I'm taking one more triangle, that is from the previous figure, this triangle. Okay, with respect to image. So this is the image, and this is one more right angle triangle. From this also we can write tan beta as h dash by this distance is called the tube length. This is a tube length of the tube. Okay, so distance between the f naught and fe is the length of the tube here in this case. So from this we can write tan beta is equals to, this is the tube length, so tan beta is equals to opposite by adjacent. So we got tan beta, another expression for tan beta as h dash by l. From by combining these two expressions we got h by f naught. H by f naught is equals to h by l, and by simplifying it we will get h dash by h is equals to l by f naught. So what is the magnification formula? M naught equals to h dash by h. Therefore the linear magnification produced by the objective lens is about l by f naught. So this is only the magnification produced by the first lens, objective lens. Okay, now there is another lens, that is eyepiece, the lens which is close to eye. Now here uh, look at the previous figure. Here the object to the first lens, so here the image of the first lens will act as an object to the second lens. So this is the image. A dash B dash is the image formed by the first lens. The image of the first lens acts as an object to the second lens. Here this object is not exactly on the focus, it is somewhere below the focus. Okay, here this is the focus, position of the focus, and we have adjusted the lenses such that the image of the first lens is formed just below the focus of the eyepiece. Okay, now the image of the first lens acts as an object to the second lens. Okay, since it is little below the focus, the image is formed on the same side. We have adjusted the distance between the lenses such that the final image is formed exactly at the near point, 25 centimeters. Okay, now in the previous case we have discussed when the image is formed at infinity, what is the formula to find the magnification? So what is the magnification formula? It is 1 plus d by fe. No need to derive it again, already in the previous simple microscope we have derived. The magnification produced by the eyepiece when the final image is formed at the near point is 1 plus d by fe. When the image is formed at infinity, the magnification is 1 plus and simply d by f. Now it is 1 plus d by fe. Okay, we got two magnifications. So when the image is at infinity, we will get d by fe. When the image is formed at near point, 1 plus d by fe. Okay, therefore the total magnification produced by the compound microscope if the image is formed at infinity can be written as the product of the individual magnifications. Okay, therefore total magnification is m is equals to l by f naught into d by fe. ME is taken as d by FE when the image is formed at infinity. When the image is formed at near point, we can replace it with the 1 plus d by FE. Okay, so this is about the compound microscope. Let us take an example. So I want to know what is the amount of magnification uh, produced by the compound microscope. Let us take a compound microscope. The focal length of objective let it be 1 centimeter and focal length of eyepiece about 2 centimeter and the tube length L is equals to 20 centimeter. Now we have to find out its magnification. Okay, so here what is the formula? M equals to M naught into ME. M naught is nothing but L by FE. Magnification produced by the objective lens is L by F naught and eyepiece is D by FE. So L F naught D, and what is D here? Near point is fixed. It is about 25 centimeters. It is 25 centimeter. Now, all are given to us. Simply substituting all the values, 2 tens, I will get a magnification of 250. So here the size of an object is magnified by 250 times. Okay, huge magnification. We will get huge magnification with the help of this compound microscope. But with this objective lens, if you take objective lens, what is the magnification of objective lens? It is on the order of only 20. Okay, so this is about the compound microscope. In the next class, we will discuss the telescope.